wake up either one of these devices or the other, as can be seen here. And then I said, well, you might come across the term block address decoding. And block address decoding is a form of partial address decoding, but where the aliases are confined to a certain region of the memory map. So here was an example of that, where you can see I'm going to have aliases because some of these address lines are not being used by the address decoding logic. But I'm using more than I did for that very simple partial address decoding before. And in this particular case, you can work it out by hand. You'd end up with a memory map that looks like that. So now I do have aliases, but they don't appear all over the place. I still have parts of the address space which is free to be used by adding other devices later on. Now let's say you wanted to add a device that's active in this memory range down here. You would have to, if you like, design the address decoding circuitry so that when those combinations of address values appeared on the address bus, the device would be awake. It's your job as the designer to engineer your decoding to achieve that. So that's where we got up to last week. I'm going to go quite quickly because we've still got quite a lot of material to get through this course over the next couple of weeks, and we haven't even started this week's topic yet. And we've still got another topic to do from last week. So if having gone through this material, by the way, and you're not clear about what I'm saying, remember I do have those office hours on Thursdays, that's today. 2 hours of office hours, so you can always come along and ask questions then anyway. Anyway, someone actually asked me after the lecture last week about, well, why am I using discrete logic gates? You don't have to. Here's an example of address decoding which is achieved with a medium scale integration device called a data selector. So in this particular device, it has 3 address inputs, which gives you 2 to the power 3 different combinations. And for each combination, 1 of 8 outputs goes low. The rest of them are guaranteed to be high. So you can use this kind of circuit for address decoding. So what I'm doing here is feeding in 3 of my address lines into this device. Of the 8 outputs, only 1 of them is guaranteed to be low at any point in time, which I can use to switch on up to 8 memory devices in this case. This would give you a form of partial address decoding here because I'm not using all the address lines for the address decoding. So we will get aliases, but they'll be confined to a certain region of memory. It's going to be some kind of a block address decoding, probably. I don't think I've got a memory map for that. Right, here's your worst nightmare address decoding scenario. Okay? It doesn't get any more horrible than this. So you're a designer, and you're working for a company, I don't know, ARM, Motorola, Philips, I don't know, something like that, and they said, okay, we have this device that's going to be attached to an address bus. Other things are already attached to this address bus, and we don't want to have any conflicts with what's already connected to it. This device is only allowed to be awake for 5 combinations of address value. And they tell you precisely which 5 address values this device is meant to be awake for. It has 5 internal registers, as you can see, so we've got 1, 2, I don't know which one it is, 3, 4, 5 values. And to start with, we will assume that every other possible combination of values on the address bus, this must be asleep, okay? It must be asleep because for all other combinations of values on the address bus, they might be used to wake up other devices. We don't know, okay? We've been given the task to do the address decoding so that only those 5 combinations will wake up this device. So for now, we're going to assume these are the 5 values that must wake it up. There are other values which are different here, only in the lowest 3 bits, but for now we're going to assume that they're illegal, they're values that should have it asleep, along with all other values on the address bus. So how do we achieve address decoding? So here's the device. These are the address lines which are feeding into the 5 internal registers, which are used to select particular registers. But we're also using the whole of the address bus into address decoding circuitry. And for each of the 5 values, if I go back one slide, there's this one, this one, this one, this one, this one. These values are going to appear. This is just one of those combinations here. Okay? And this chip enable goes low when the device is awake. So what we're doing here is effectively we're feeding. Now this, what we're doing, we're bringing all this in. Now there's 5 different addresses where this has got to go low. This particular slide is only a 1/5 of the address decoding logic. This is the address decoding logic needed to make sure it will pull this pin low if this combination was to appear on the address bus. The next slide will deal with another combination. So these from part B, part C, part D, part E are from the next 4 slides, different combinations that would basically feed into this NOR gate to pull this low. Okay, so this is just the first combination. And what we can see here is high, high, high is basically we're just taking those, when those are all high. Basically, in order to pull this low, this input has to be high. If this input here goes high, or any of these inputs go high, it will pull this low. It's an OR gate with an inverter, okay? So, remember if you've got an OR gate, any input high, the output goes high. So this is an OR gate, so any input goes high, the output will go low, okay? Did that in year 1. So we're looking at one combination here that would pull this AND gate high. And that corresponds to this address here. So it's a ridiculous AND gate. It's a 16 input AND gate. You're not going to find a 16 input AND gate, but just pretend you could. So if this combination was to appear on the address bus, you'd have a high, 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 high. The next values go high, low, low, high. High, now that would be low here and low here, but we've got 2 inverters here, which means that when that combination appears here, all of those 4 will be high. Okay? Then we've got low, high, high, high. Well, the low here will make that go high, so it'll be high there, high there, high there, high there. So all of those will be high. And then the lowest 4 are all low, but they feed through 4 inverters, so they'll all be high. So for that particular combination, when that appears on the address bus, all 16 inputs to that AND gate will go high. Which means the output of the AND gate will go high, which means that feeding into the NOR gate, it will pull the output low, irrespective of what anything else is happening. It will be guaranteed to pull this low and wake up this device. That's one combination. This is a second combination that's feeding into that previous slide. And here's the second set of values that we must use to wake up this device. So high, high, high here. So there's those 4 feeding into those 4 inputs of the 16 input AND gate. This is a different AND gate to the one on the previous slide. Then we've got, where are we? High, low, low, high. So then the highs come in here. The inverters here will take those 2 lows and make them high at this point. So you'll end up with 4 highs here. Then you have low, high, high, high. Well, there's that low, but it's going to be inverted to make it high. So they'll all become high. And with this particular combination here, low, 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 high, that's going to be inverted to become high, 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 and that's a high. So they all go high for that combination. So if that combination appears on the address bus, the output of this AND gate will go high, which will be another means of pulling down that NOR gate and making it go low, waking up the device. And the same goes for the next 3 slides. You can see, if I whiz through them, there's all 5 of them. The only difference between them is actually in terms of a few inverters down here. Yeah?
So can you, the 3 lines that don't change, you could.
Yes, and I'm going to, well, I'm going to simplify it over the next slide, because this would work, it would solve what we've been asked to do, but it's not in the slightest bit elegant. This is the brute force, horrific way of solving a problem. For a start, you're going to need 5 lots of 16 input AND gates. And then you're going to need an awful lot of inverters, and then a 5 input NOR gate at the end of it. I'm not even sure you can get a 5 input NOR gate. So you can make these things up by cascading smaller devices. But in terms of the amount of combinational logic in total, it would be a lot. It'd be a very tedious way of solving this problem. But it would work. An alternative way is, if you look at those 5 previous slides, you'll notice that in terms of 12 of the 16 inputs, they didn't change for all the 5 different combinations. The only changes were in the lowest 3 bits on the address bus. Well, we can use that to our advantage, because we can basically now, okay, it's still not a simple design, but now instead of 5 16 input AND gates followed by a 5 input NOR gate, we've simplified it down to a 16 input NAND gate, a few inverters here, and we're going to use a bit of year 1 Carnot maps to come up with some simple combinational logic for this to put in here. Because we're basically saying this device has got to wake up when this holds true, when the upper 4 bits of this value, the next 4 bits of this value, the next 4 bits of this value, bit 3 has this value, and it's only combinations where it says K that wake up the different 5 registers within the device. Well, doing a truth table, remember not all 8 combinations are valid, only 5 of the 8 are valid to wake up the device. There's the truth table showing the 5 values here, which are the ones that need to wake the device up, and the other 3, it's got to be low. Okay? Well, express that in a Carnot map, and then get your equation from it. That's the simplest equation you can get from this map. And it's basically not A0 ANDed with not A1, ORed with not A2, which would be this. I don't know if I've got that on a... No, it doesn't show it. So you could basically, this little circuit here would be in that little green block there, and you'd achieve everything that you would on those 5 previous slides. Yeah?
Is Carnot maps going to be an exam?
Is it going to be in the exam? You are expected to know how to do Carnot maps. Whether there is one in the exam this year, I can't say. But it's a year 1 thing, so you know you all did DCD, I hope. So you're expected to be proficient at Carnot maps. And to be able to write truth tables for simple logic gates like NAND, NOR, AND, OR, and that kind of stuff. Okay, so if you're a bit rusty on those things, then you probably need to brush it up. Okay, so that's one way of solving this problem. It would achieve what we've been asked to do. Even so, it is still quite horrendous, because I'm still required here to have a 16 input NAND gate in this case. But you're not going to be able to buy a 16 input NAND gate. So we'll look at ways of solving that. This is a not very elegant, but an alternative way of doing address decoding. Just want you to make you aware of it, where we've used an EEPROM to provide the address decoding logic. And what we've done is we've written into the EEPROM, and this is a 64K EEPROM, because the address bus here has 64K different combinations, and only 5 of those 64K combinations have D0 value low. And this could be an 8 input, an 8 output EEPROM, so there'd be a D1, D2, and so on, but we're ignoring all of those. Remember, an EEPROM, what we've got something that's 64K in this case, And each of these locations is D0 all the way up to D7. And almost all of the D0s, all the way through this thing, are all set high. But the 5 combinations where we want this device to wake up, we've set those D0 values to be a low, but only those 5 combinations. So only when those particular 5 combinations appear on the address bus, this EEPROM will make D0 go low, which will wake up that device. Now, in days gone by, EEPROMs were very expensive, so this would not have been a viable solution. But nowadays, EEPROMs are relatively cheap, and actually almost the same kind of price as discrete combinational logic. So nowadays, it may well be more efficient in terms of saving space and no kind of penalty in terms of cost using something like this to perform your address decoding. The nice thing about this is you can easily program it to have any kind of combinations to wake the devices up, and if it's an 8-bit EEPROM, you could use it to control 8 separate peripherals. Okay. Another thing we could look at is, now we've so far assumed that only 5 of the 8 combinations down here are legitimate, and the device has to be asleep for the others. If we relax that restriction, let's go, I'm going to whiz back lots of slides just to remind you. We assumed that it had to be awake for these 5, but asleep for those. If we say it doesn't matter if it's asleep or awake for those, all that matters is that these bits up here have this particular value, and if the device is awake for these combinations but it's not going to actually access a suitable register inside the device, it doesn't matter. We can simplify down the design a bit further. So that's this last thing here. So now you'll notice that these 3 lines here, A0, A1, A2, are being used to identify the different registers within this device, of which there are only 5 of them. And we're assuming it only had 5 internal locations. There are 8 combinations here. But we're going to assume now, for the other 3 combinations here, it won't do anything damaging to this device. It's not going to matter. And that nothing else connected to the address bus cares about those 3 values, provided this all holds true. So we're only using 12 lines of the address bus now to do the address decoding. Is it 12? No, 13 lines.
Right now.
16 take away 3 is 13. So we've now simplified the address decoding to this, so that now this combination here has to appear on the address bus in order to wake this device up. So it's 111, 1001, 0111, 0. So when the address bus upper 13 lines have that particular value, this device will wake up because this address decoding circuit will pull that low. And then A0 to A2 will determine which of the registers in there we're talking to. The only downside of this approach really is there are 3 combinations here where this device will be awake, but those 3 values don't have any meaning in terms of accessing internal registers in that device, because it only has 5 registers, not 8. Okay. You can't get 16 input NAND gates and 16 input NOR gates. Try. What you can do is you can cascade simpler gates to achieve the same effect as a high fan-in gate. So here's an example for example. Here's an example for example. Here's an example of a 3-input NAND gate, and we've achieved the same logic function using only 2-input gates. In this case, an AND gate followed by an AND gate. So when I drew those things with 16-input NAND gates and 16-input AND gates and 5-input NOR gates, in practice, if you were going to do it with discrete logic, you're going to have to do it in some way like this. But there is a risk with this, and I want to briefly talk to you about this risk. And let's take an example. So let's consider briefly this circuit. Let's check I got it right. Yeah. And let's do the truth table for this circuit. Okay. So we've got A, B, X, and F. Okay. Well, there are only 4 combinations of A and B, so let's just get those out of the way. X is just the inverse of A, so it's going to be... Okay, so far so good. And then this is an AND gate. So an AND gate, if it was an AND gate, the output would only go high when both inputs are high. It's an AND gate, so the output only goes low when both inputs are high. So we're looking at the inputs of B and X. So only when both inputs are high will the output go low, which is only that combination. And it'll be high here, and high here. Anyone disagree with me? Right. Now let's consider the situation when A is low and B is low. Well, A is low, B is low, F is high. Okay? And let's consider the situation now where A is high and B is high. A is high and B is high, this is high. So, if the address bus happened to switch from values where we went from low, low to high, high, we would expect this to remain high the whole time. Bad news is that's not true, because this has a finite propagation delay. So if we went from low, low to high, high on these inputs, for a short while, when this goes from low to high, this 1's going to appear here almost instantaneously. This is just a piece of wire. But this low to high, it has to go through an inverter that has a finite propagation delay. You know, if you like, delta t. So for a while, X is still going to be whatever the value is here. So it was low here, so this is going to be high for a bit. Eventually, remember, it started off being low, which means the output of the inverter was high. That was the initial thing. And we've gone to a state where it's going high. So this will go low at some point, but it isn't going to happen straight away. Okay? It's going to happen after delta t. So for a while, this is still high. But this has gone from low to high. And it's going to happen almost instantaneously, the speed of light. So you're going to end up for a situation where temporarily, where are we? X and B are both high for a little bit. This combination. So in fact, what you'll actually see coming out of this circuit is it's going to be high and it's going to drop down and then go up again. And this dip is going to be the duration of that propagation delay, which could be quite a few nanoseconds. If this was connected to something like, I don't know, a bomb or something that's mission critical, and pulling it low detonates the bomb, now you might think, oh, it's all right, it's perfectly safe. I'm going from low, low to high, high. It's all going to be fine. I'm not going to be standing anywhere near you when you build this circuit because you're not going to be around. This is known as a glitch. And it's a well-known problem with address decoding circuits, where the path feeding into the address decoding logic on, if you like, the length of different paths is not the same. Okay? So you'd be expected to know in this course about this problem, and that it can give rise to glitches. The solution to the problem, because this is, you know, it happens, is you might say, what we'll do is, if we have address decoding logic feeding into some kind of device, like a memory device, what we could do is, first of all, put on the address bus here whatever values we want, wait a little bit of time until this kind of settles down, and then we'll access the device and we'll do something then. We'll do something with the device then. So that might mean you might gate the chip enable through a clock, or you might do something else. But basically, you don't drive this device purely from the address decoding as is. You know, I might gate it through an AND gate with a clock kind of thing feeding in here. I let this settle, and then only then do I fire the clock pulse. That would be one way of dealing with it. Sometimes you have different... Now, it sometimes doesn't matter, these glitches, but sometimes it can matter an awful lot. Okay, so that's one thing I wanted to mention. Let's just review the memory map for a minute. We've been talking about address decoding, which is how we can organize different things inside the memory so that only one device is awake for any particular compilation of addresses. You would certainly be expected to know about the complete memory map of the 8051. So this is a kind of summary slide. You've seen it before. Let's go through it again. So over here is all the memory that's on the 8051 itself, or an 8052 for that matter. And over here is external memory. Okay. In terms of the internal memory, there are two types: the code memory, the program memory, and the data memory. The data memory, the lowest 128 bytes, includes things like the register banks, a block of bit addressable memory, and then some general purpose memory. The upper 128 bytes is where the special function registers sit. If you happen to have an 8052, in parallel with the special function registers, there's another block of data memory that's general purpose. It sits at exactly the same memory locations as the special function registers. And we're able to achieve this because we have instructions that we can use to access these, and a different set of instructions that only work here. So it's implicit in the instruction, are you trying to talk to this set of memory, or things over here? If you do direct addressing, you always talk to this. If you do indirect addressing, you always talk to this. Indirect addressing, for those of you who don't remember, is addressing where you might say something like, use the contents of R1 as a pointer to where you want to go to. R1 isn't the thing you're trying to get to. R1 contains a pointer to somewhere else in the internal data memory. Indirect addressing. If you use that kind of technique, you'll end up here if it exists. Yeah.
So the value in R1,
yeah,
it would read it as the data.
It would, if it's a value less than 128, it will get you into here. If it's a value more than 128, it will not go into here. It will try and get to here. Now, if you've got an 8051 and you do that, I'm not sure what's going to happen. But with an 8052, you would get into here and not here.
But if you specify that address directly, it goes into...
If you do it, now if you say, you know, move into the accumulator, the contents of, no, don't do R1, let's see. I don't know.